Good, okay. So thanks for coming for my last lecture. So what we talked about the previous couple times, to remind you, we covered an introduction to formal methods, and we've seen a lot about reachability. Last time we saw some runtime verification, so for monitoring what autonomous CPS may be doing. And the previous talk was a great sort of refresh and a nice overview of what this may look like within the context of autonomous CPS. So now this talk I'll cover some more recent work that's been emerging in the formal methods community, some of which we've done, some of which other people are doing, primarily that is focused on trying to analyze neural networks to determine what they may do in a verifiable way. So feel free to stop me. Of course, so our context, again, we're trying to verify properties. In this case, some of the systems that we'll look at may be neural networks or other data-driven components that have been trained from data using machine learning methods to be able to generalize from that data, and also their usage within closed-loop systems. So within this talk, A is now going to be a neural network in one case, so that's what I'll talk about first. And in another case, A will be a closed-loop system where a neural network is being used to control some plant. And then at the end, if I have any time, I'll talk about some more general specification languages for what our properties may be. So I have to use the word property carefully because property sort of means something specific with respect to executions of systems, but there are generalizations of properties such as hyperproperties. So if I have time, I'll cover some of that. Good. All right, so this is our prototypical architecture that we're working with. So last time in the runtime verification framework, we were trying to essentially monitor what a controller may be doing. So now what we're going to try to do is actually do some analysis of that controller under an assumption that it is a neural network. So that's one way to do this. This perception problem, which is where a lot of the deep learning type of stuff is showing up within CPS, this is still, I would say, uncharted territory. Nobody really knows how to do anything to rigorously analyze those types of components, and that's what's illustrated by all of these recent adversarial machine learning attacks, where you can, say, trick an image classifier to misclassify an image or video input signal. So now we're talking about design time instead of runtime. So last time we talked about runtime. We're going to talk about design time now. So this would be something we're doing a priori. So there are some limitations of this. I'll talk some about scalability, whether we can have formal models at all. So this may not be possible, but in some cases it may be. So we'll talk about what the community is doing within this. So just to remind you, this is what we did last time. So essentially a supervisory control where we'd monitor whatever some complex, maybe machine learning-based controller is doing, and then deciding whether to take safe actions or continue using actions from that complex controller. So part of the background for this is in the survey, so if you're interested in this we'll hopefully have an archive soon, but this kind of covers what all the state of the art is in verification for machine learning-based systems with a focus on autonomous CPS. All right, so let's see what's happened pretty much in the last 1 to 2 years. So this area is sort of exploding within formal methods, in part, I would say, for a couple reasons. One is all of the hope that autonomy may bring, perhaps a little bit overhyped right now, but just the broad applications of machine learning methods, particularly that may show up in safety critical systems. So in doing image classification and other perception aspects of things like autonomous vehicles, but other systems as well. So this is pretty much all of the tools that exist in this space now. And there's more. This is coming out of our survey paper. So at CAV in last year, this ReLUplex tool came out for analyzing neural networks with a form of linear activation function. And I'm going to talk a little bit more in depth about neural nets shortly and tell you what that is. So after this, there was another CAV paper in that year. Then we've sort of exploded with a lot of different approaches. Many of these are based on solving linear programs. And those typically are going to be restricted to these piecewise linear activation functions, which are these ReLUs. And I'll show you exactly what that looks like shortly, and you'll sort of understand why you could maybe formulate this as a linear programming problem. There are also some satisfiability modulo theories approaches that are being explored, or combinations of these two things. So there are a couple outliers maybe. One is this abstract interpretation-based tool called, of course, cleverly AI squared. Right, artificial intelligence, abstract interpretation, so it's kind of nice. Then we have some approaches. So our maximal sensitivity approach, which I'll talk some about, this, as far as I'm aware, is the only approach that currently exists for analyzing activation functions beyond ReLUs. So this can work for other nonlinear activation functions. All right, so papers on this we'll skip over. All right, so how do we do this? And how do we formulate this problem? So what are the components we're looking at? So we're working on these data-driven components. So a learning-enabled component has been trained using data. So whatever we want to do, typically a priori, we'll have specified in some way, perhaps just with data itself, perhaps in an ideal case with a more formal kind of specification. So after training, though, we have these components, and then things look pretty good. Performance looks good, but perhaps we do still have these edge cases, right? So these are the things that are being illustrated by adversarial machine learning, and I'll talk about what that means in the context of neural nets in just a minute. So the objective, of course, would be for whatever the input space is, make sure that we're going to meet our specifications. So the standard verification problem. So the reason perception right now seems so difficult, if you think about the input space of, say, an image classifier, well, that's the space of all images of some certain size, right? And now if they're black and white or if they're color, the input space for that is going to be huge. So we'll talk about some simpler cases for smaller networks. All right, and a bunch of challenges that are going to exist. So feel free to stop me if anything doesn't seem clear. So the context of what we've been doing so far would be if we're using neural networks within feedback control systems. So we're controlling some plant, and this is a kind of discrete time formulation, but you can generalize this. And then we have a neural network-based controller that's looking at outputs from the plant, so taking sensor measurements. Maybe it has a signal you want to track, or maybe it's got some noise. Maybe the plant has noise too. And then we're going to come up with a new choice of control action by looking at the plant state that we've measured and either a reference signal, maybe we're incorporating noise into this, and then come up with a new control input for the plant by essentially shipping this through a neural network. So this is kind of an old style of control, intelligent control that was very popular in the 90s. But this is our setup. So what our controller is a neural network. So for feed-forward neural networks, we can just view this as a function that's going to map from some space, in this case the space of plant outputs, to the space of plant inputs. So mathematically, I can just view this as a function. So I'll come back to that point in just a minute. So these types of controllers can be used in adaptive control. Maybe we've done this because we have some uncertainty. But how we're going to do this, the analysis of this within the context of a feedback control system, is that we're going to alternate computations of analysis of the neural network and reachable set computations of the plant. So we've seen a lot of talks in this summer school so far about how to do reach set computation for, say, differential equations or hybrid automata. So we're going to alternate these two things. So we've seen some on how to do this second step already, so I'm going to talk about how to do this first step. So how do we do this? So if we think of the neural network, if it's a feed-forward network, just as a mathematical function, then essentially we're doing a range computation, right? We're trying to estimate the range of that function. So we're going to provide a set of inputs to that function, and we'd like to see what the set of outputs are. So this formulation isn't going to make sense for every type of machine learning problem that you could formulate, but it can make sense in some contexts, such as in this type of feedback control system. So just briefly on neural networks, I assume most people know roughly something about neural networks. So some biological inspiration model. So you have some input neurons. So these are going to take, in our case, think of all these as reals. So they're going to come in, we have some weights, maybe some other ways to transform these. So we're going to sum these things up. And then if a certain condition of this activation function is true, then we'd activate those and apply the activated neurons as this type of function to produce whatever the output would be. So let's come up a little bit there. And so we may have a lot of layers in this for which neurons are getting activated. But mathematically, if you sort of see what's going on, we have input and we have output. Right? So this is coming from some set or some space, and that's going to be produced in some set or some space. So the classes of activation functions that are commonly used, there are a variety of them. Some of them are kind of nonlinear. This ReLU activation function is commonly used, and as you can see, it's just a piecewise linear function. And it's simply defined as just being 0 if the input to this is 0. Otherwise, you just produce whatever had come into the function if it's beyond 0. Okay. So we may hook up these things together into networks. So there are some nice properties of these. You can approximate any functions with finite number of neurons, some nice various properties. But as we get these things quite large, it's very hard to understand what they're going to do. So what are we doing? So how are we going to do this range analysis problem, and what does it mean? So let's suppose we have a feed-forward network. So again, a mathematical function mapping from some input set to some output set. So we would like to now compute what the output set can be provided some input set. So mathematically, what we're trying to do essentially is to compute the range of this function provided some set of inputs from the set of all possible inputs. So how does the network transform this set as it passes through? So for this to be scalable at all, and how most of these approaches essentially are working, is we'll represent the input set as some form of polytope. So for this case, right, I have, I don't know, 7 or so inputs. So I have some 7-dimensional polytope. Right? And let's suppose that, it's polytope, there's convexity things, and so on. So then I'm going to take that polytope and I'm going to propagate it through applying whatever functions exist within the hidden layers. And then at the output, hopefully I'll have a polytope or a union of polytopes. So basic problem makes sense. So essentially, there are different terms for this. This is a range estimation problem or a range over approximation problem. But essentially, this is some complicated nonlinear function, in essence, kind of piecewise nonlinear for this ReLU case. So we're trying to see how is that function going to transform a set of inputs. So in the context of verification, what we can do is have some input set and check if wherever we can get to in the output set would intersect with some other predicate over the output space. So this would be a standard kind of safety verification problem. If you want to make sure, for example, that the neural network controller can't produce an output of some certain value, that may be an interesting problem for you, and that would be this kind of safety verification problem. So let's talk about the ReLUs a little bit more. So there are a few ways to define this function. This is another way to do it with a max. So what these ReLU type functions can do is be active or not. So they're going to essentially propagate something at a particular neuron or not. So because of this piecewise linearity, we can establish the following result, which we can use to enable layer-by-layer propagation. So the lemma or theorem of this essentially is, if our inputs are a union of polytopes, then our output for any layer will also be a union of polytopes. And the way this transformation is working for any particular neuron, it's just taking whatever it was, so if it was linear, or it's taking 0, right? So it's really not doing too much transformation. Maybe if it's 0, we're sort of going down to some smaller subspace, right? So maybe the polytope has been transformed. But in a planar way, the way you can see this intuitively is if we have a union of polytopes, we apply the ReLU network to it, we'll get some other union of polytopes. It may possibly be more polytopes. So you can do this with essentially each one at a time, but we may end up producing more polytopes than we started with. And that's essentially based on this case breakdown of if the ReLU neuron is going to be active or not. All right, that kind of makes sense. Okay, so that's a property that can be exploited. It turns out this is exact for ReLUs, so you actually have no over-approximation. So you can do this exactly for ReLU networks. So that's what our approach does. Other approaches may incorporate some abstraction that would make it non-exact. So how am I on time? I've been going, what, 20 minutes or so? So another 25 minutes? Okay. So I'm going to skip over a couple of the details of how this works. But essentially, we wind up with different cases for if these ReLUs are active or not, for if we're going to zero things out. So in the worst case, we could have an exponential growth in the number of polytopes. So that could be bad. That's going to limit scalability of this. But I'm going to skip through this because I want to talk about the other approach a little bit and show you just kind of pictorially what this can look like. So this is a numerical example. So we have a ReLU network with 3 input neurons, 2 output neurons, 7 hidden layers with 7 neurons each. And the input set that we're analyzing or looking at is this kind of unit cube-like shape, so some 3-dimensional box. And what the pictures are that we're looking at here, the output space has 2 neurons, so it's R2. So we're looking at this planar view. So we have this box type of input, and then this is what the output is, right? So because of some of the neurons being activated, some of them not at different points, we wind up with this sort of weird transformation of that cube that we provided as input. So you can see this thing is now non-convex, although it's a union of convex polytopes. And this is just kind of a validation of applying inputs randomly from that input space, just to further illustrate that, yes, this is sort of over approximating everywhere we could go to in the output space. All right. So let's come back a second and talk about how to use this within feedback control systems. So we have this neural network-based controller here, and then we have a plant. So we're going to produce some inputs for the plant using that neural net controller. So we'll look up at a time-bounded set of reachable states. In this case, we're assuming things are linear for this controller, or for this plant as linear dynamics. And then the control is whatever that ReLU had done. So this is just a definition of essentially a time-bounded reachable set up to some k discrete units of time. So what you can do then, sort of the natural intuitive thing to do, is to alternate iterations of computing the set of reachable states of the plant and of the controller. So we know what the controller is going to do, provided a set of inputs. That's what I just talked about with the range output reachable set computation or range estimation problem. And then we also know how to do reachability analysis for plants of this form, or if this is ODEs or whatever. So we know how to do that. So we can just combine these and alternate how we're going to be, we'll alternate the computations of the neural net controller output reachable set with the plant reachability computations. So this is some description of that, and we'll do this up to some time bound. So what we'll do is at some initial state, we'd have an initial state for the controller and for the plant. So we can start this out in either mode and essentially, but let's just suppose we have some initial states for our plant, and our neural network controller is defined. So if we have some initial states for the plant, we can determine what the plant's going to do over a time interval, so over the next time step. That's going to do something that's going to produce new outputs. Those outputs are going to get fed back in as inputs to the neural net controller. And then we can perform from that. This would now be a set, because all these computations are going to be set-based. We would determine where the neural net controller could take us, right? So what would the output be provided that set of inputs? Then we can now, this would then be a set of inputs for the plant. We then take that and then propagate that through and repeat. Kind of makes sense? Questions? Yeah.
Each iteration is moving forward one step at a time.
Yes,
So
yeah.
you have a delay in the middle.
Yeah, yeah. Yeah, so you could imagine this being done like, you know, if we were in real time instead of discrete time, if we're in continuous time. So we do this like delta time, you know, in chunks. So assuming the controller is being executed periodically.
How is the final choice of the action being decided? So you have a kind of a reachable state. So you need to pick up one of these for the final action.
Well, so if we're really running it, sure. But for analyzing it, we don't have to, right? We're actually using the whole set. So so the action we'd be picking essentially is what is U.
So plan the behavior updated for all possible actions.
Right, within that set, yeah. And essentially the reason you can do this is all these reachability methods for hybrid systems or for ODEs or set-based computations. So all I'm doing is providing now a set of inputs to that. Yeah, so we're essentially choosing all possible actions in that set.
This is a little bit like assume guarantee.
It's not the same time. There's a sample and hold.
Yes, but normally it should be the same, right? It's like at the same time the U action U will change the Y. Y will change the U again.
In the next time.
The next time step, there's a delay.
But
Yeah.
Not in this picture.
Yes.
Not in
Yeah, maybe not in the picture, but yeah, yeah.
He has x of t plus 1 in the plan. Is a function of vector.
Yeah, so this would be like the previous round's controller value. Yeah, but it's, yeah.
But you're right, if it was forward,
yes.
then
Yes,
it would be a fixed point. You have to have a fixed point.
Yeah, I typically think of that in kind of like an axiomatic basis, and this is more like, you know, reachability, but yeah. Okay, all right. So that's the basic idea. There's another numerical example that I'll just show you some pictures of. So if we had some input set, again, some kind of cube, in this case in R2, and again, let's say our output or our state space is R2. We could do this type of computation up to some number of time steps. So in this case, we did it up to like 5 or 6 time steps. And if we had some safety property that we cared about, we could just do the normal thing and check intersection of our reachable states with that, see if it's empty or not. So there's some methods to reduce computation time that I'm going to skip over, but how to make it a bit more scalable. So I'll switch gears a little bit now and talk about more general activation functions. So most of the tools that I listed earlier are targeting ReLUs, and some of our work has as well. And in part, they do seem to be fairly widely used, although there are other activation functions that are also used a lot. So a natural thing to do is how can we generalize the class of activation functions? And things are going to get harder if we do have a more nonlinear activation function. So that kind of key property of the ReLU that's being exploited is that it's essentially piecewise linear, right? So we got that nice polytope propagation result that if we had an input of polytopes, our output will be some union of polytopes. So that's not necessarily going to be true if we have some other activation functions, right, depending on how the transformations are going to work. So we'll talk just a little bit about how we can do that. It's a similar type of idea. It's a sensitivity type analysis of the feed-forward network, again, thinking of it as a function. So we have some point that we're going to take and send through the network, and that should map to some other point. So in an actual concrete execution, this is what would be occurring. So again, we're doing this design time analysis, so we're wondering about sets of inputs and sets of outputs to try to characterize overall behavior. So if we look at a box around that point of delta width, we would like to know how that can be transformed, right? So what is this set going to look like? So we can characterize that distance, again, assuming, say, it's a box around that point, with some other width, in this case, epsilon. So this is kind of trying to characterize the robustness of this as a function. And when you think about what these adversarial machine learning examples are illustrating, they're essentially illustrating that in many cases, whatever this neural network is doing it's not robust, right? So some of the examples from adversarial machine learning are things like I'll change a single pixel, and now my image classifier will, instead of saying I see a person, I see nothing, right? And obviously that's not real, right? I mean, you wouldn't be able to say there's a person in an image by being capable of changing a single pixel, and all of a sudden now they're not. So essentially what that tells us is that these functions are not robust. A small perturbation in the input space results in some discontinuous large change in the output space. So this is a definition that can be used to characterize how big of a change is there in the output space, provided some set of perturbations in the input space. So that's kind of the motivation of this type of an approach. So we could then more finely do this. So if we over-approximate some set of inputs with a bunch of these boxes, any of the points within each of these boxes would be at most delta away, right? Any point here is still at most delta away from the center point and so on. And then what's going to be the set of outputs we can get to. So I'd like to over-approximate this. So in contrast to some of the ReLU results, now this is over-approximative and wouldn't be exact, in part because we're relying on this polytope or even more restricted box-like form of the state space representation. So this can be done, this can be formulated as an optimization problem of how far away we are subject to some constraints, right? So I can formulate that distance of any point from a center point, then some definition of what the function is actually doing, and how the outputs are kind of nicely defined. So this is the characterization of how far epsilon we can get away. This is actually that mapping, right? And then what we're trying to do is come up with a maximal choice of that epsilon provided delta that we can get away, right? So we're going to see how big can that possibly be. So some possible issues with this, depending on how philosophical we want to be with the formal method stuff. We're now solving an optimization problem. There may be some numerical issues, but at any rate. So that's a nonlinear optimization problem. It looks sort of nasty. There's some ways to turn it into a convex optimization problem that I won't go into all the details of, but we can do something to transform it to make it a little bit nicer class of optimization. And I didn't clearly state on a slide a couple back, and I want to go back and do that. Yeah, so the assumption that we're working with on the activation functions is this kind of monotonic assumption, right? So any activation function satisfying this assumption can be analyzed. And this essentially is saying that the activation function is somehow monotonic, right? So if we have a point as an input to it that's smaller than some other point x2, then the output of the function also satisfies that constraint. And that assumption is part of what lets us do some optimization in this process, right? So we're applying that assumption here. Okay, so that was for a single layer. You can then repeat this process for all the layers, see how this thing's going to get transformed. Obviously, because we're solving optimization problems now for each layer, the scalability of this may be quite bad. But still an interesting approach to characterize the behavior. So this numerical example now, we have a couple inputs, a couple outputs, and 5 layers with 10 neurons each, and now we're using the tanh activation function instead of ReLU, which would satisfy our monotonicity assumption. So we have our input set defined like this. So our delta choice is 1 or 0.5, depending on this, how it's defined. Okay, sorry, so we're actually gridding over on top of this with our choice of delta. But our input set is this kind of unit cube. And what we're seeing on the output are various choices as we're making delta smaller and smaller to characterize more precisely where we could get. So we fix delta, then we're trying to find epsilon such that we satisfy that optimization problem, that constrained optimization problem with all those constraints met, essentially to try to guarantee that it's sound, right? So we're over-approximatively doing this. But as we do slice this up more finely and finely, we're getting, kind of closer and closer to what that function really could be doing. And then again, we have some simulations illustrating how this would be transformed, superimposed on top, showing that what we've computed for this choice of delta being 1,000th, those concrete inputs that we're providing do get mapped inside of there. And as we can see again, now our estimation of this output reachable set is non-convex and sort of a bit weird looking. So there's some strange transformation happening through this network. Okay. So I have about 10 minutes left. Any questions before I go on? So I talked about 2 different approaches, this maximal sensitivity thing for characterizing the behavior with non-ReLU activation functions, satisfying that monotonicity assumption of the activation. And then before that, I talked about some methods to compute the output reachable set of a ReLU-based neural network. So then how can we use these things? So we have a few other examples, and I think I'm going to skip through some of this, but we've applied this to a variety of other examples, some adaptive control type examples, where you can sort of imagine as we're pushing steps forward in time, is how we'd like to be characterizing this, kind of like the flow pipe computation that we've seen in some of the other lectures in the summer school. Okay, so I'm going to pop up just a little bit and summarize kind of where we're at and talk about some other challenges. So we've seen how to do this output reachable set computation or range estimation problem for ReLU networks. And essentially that was operations on polytopes, much like a lot of reachability computations for ODEs or hybrid systems. We also illustrated how to use this if that ReLU network is a feedback controller in a feedback control system. So it's taking inputs from the plant, which are outputs from the plant, and then producing new control inputs for the plant. That's not the only way learning-enabled components or neural nets could be applied in CPS. Obviously, another big application is perception, but I personally, I think within the community, we just have no idea how to do anything for perception at this point. I don't think anyone does. So that's a good challenge. So we saw how to do that with feedback control systems. Then we've looked at these more general monotonic activation functions using this sensitivity computation for the function representing the neural network. So that key thing in using this, the key method in using this within feedback control systems is to alternate the computations of the plant and the controller's reachability computations, which is quite natural. This is done for non-learning enabled systems. So now there are a lot of interesting questions that show up. So it may not be sufficient to consider a single iteration of the controller. So what we're looking at right now is essentially running the controller once, shipping the inputs and looking at what the outputs could do. So in path planning or something else, we may not do that. We may actually have a more detailed computation and require multiple iterations. How to scale this up for deep networks. So the numbers of layers we're looking at are somewhat reasonable, maybe somewhat deep, but the number of neurons per layer are quite low. So overall, the current state of the art within this area, across all these tools that I mentioned earlier, may be on the order of thousands of neurons at this point, whereas many neural networks may have upwards of millions of neurons. So there's a lot of scalability challenges. And I think it's not even totally clear whether we're working on, we formulated some problems here. There are some potential applications, but there are a lot of other problems within the area. So the key one, again, is perception versus what we've looked at a bit here, which is kind of control. How do you use learning-enabled components as feedback controllers? There may be more general types of AI components being used for planning and decision-making, though, right? So we're essentially coming up with a single action. What if the learning-enabled component has to come up with a sequence of actions, right? So that's something definitely that would occur in many realistic systems. Like if I'm going to drive from here back to my hotel or walk back from here to my hotel, abstractly, I kind of think of that as, okay, I got to go to the elevator first and then go down and then walk some. So coming up with that sequence of that plan or that sequence of steps, I think is a good challenge. So alternative machine learning methods. We have some ideas for how to handle recurrent neural nets, which are stateful neural networks. However, it's going to be even harder. So the way you can view feed-forward neural networks is they have no internal state. They really are a mathematical function. Now, if we look at recurrent neural nets, they may have state, right? So now they're some model of computation that's stateful. So the analysis of that is going to be a lot harder. Then there are, of course, many other machine learning methods, support vector machines. We saw some other ones like automata learning with L-star and other approaches. So automata learning is sort of nice because you get it sort of a formal model out, right? So we sort of have some idea how we could maybe analyze those. But I think, so Tom Mitchell, who's big machine learning researcher at Carnegie Mellon, gave a talk at Vanderbilt earlier in the spring. And so I'll just quote a statement from him because I'm not really a machine learning or AI person. So the statement was 99% of all machine learning right now is statistical machine learning. So it's not symbolic machine learning like L-star and some of these other things. Okay, so then I talked about if we can't solve this design time problem, what can we do architecturally to try to provide some kind of assurance guarantees? So that was what I talked about on the last lecture on Wednesday. So I think I still have a few minutes. I have some other stuff I can talk about, unless there are any questions. Yes?
Just one question about the feature definition. Maybe I have missed. So how do you define the feature for this?
Yeah, so I didn't talk too much about that point. Yes, so we haven't done anything there yet. However, if I view using features in machine learning, which is going to be used, trying to make sense of anything as you're designing it, that may provide a reasonable space of abstractions, right? Because I can think of that as sort of a simpler abstraction of what's actually going on. So I don't know, but however you'd classically do this in machine learning. So that may be another input to any of these methods.
It's basically the features about time series or these behavior trajectories. So here we are talking about. So
yeah, I mean it could be here, or if I go down the perception road, right, features are going to be line segments, or right. So it depends where we're drawing the line. Yeah. So that's kind of the idea for some of the deeper networks like image classification would be maybe we can somehow work in the feature space instead of having to worry about this thing has millions of neurons and we don't have any way to do anything with it. I don't know how to make that a sound abstraction or anything, but it's just kind of a simplifying abstraction that's already used in the design of things like classifiers. Okay, all right. So another talk for that. So one point on this is one thing we're doing within HIST, which I've mentioned previously, is we're extending specification languages for that. So I just want to talk briefly about what hyperproperties are, which are a generalization of normal properties. So a normal property or a trace property is some formula that can be evaluated on a single trace. So like things in LTL. So we can find a trace that satisfies or violates this. So a hyperproperty is, specify this in LTL, which is nice. So I can think of a trace property as this sequence of states, possibly infinitely long, depending on what the spec is. So a hyperproperty, in contrast, is a formula that's evaluated with respect to a set of traces instead of on a single trace. So kind of like a hyper set. For example, this would be some satisfying set of traces for this hyper LTL spec. So this is saying for all traces tau, there is a trace tau prime, that it's always the case that if P of trace tau is equal to P of trace tau prime, and the Q's on those corresponding traces are not equal. So let's just kind of try to understand that a little bit. So P's are equal, and then now the Q's are not equal, right? And maybe we could switch that around, and now we have not P, but always the polarity of the Q's on the corresponding traces are switched. So where these are used is within security quite a lot. Let me just pop up and talk about it another way. So if you look at a trace as a sequence of execution states, then a property, like all the properties, or if I consider all of the possible traces of some system, we can think about checking whether a system satisfies the property with respect to comparing the system's traces that can be generated, right? So we can come up with what the set would be with something like model checking, and then what are all of those traces that the property would satisfy. So I can say that a system satisfies some property P if and only if all of the traces of the system satisfy P. And essentially that's going to mean that it's a subset of this. All right, so this is sort of an interesting, I think, way of looking at this, because these traces now are possibly infinitely long, right? They're sequences. But it's very similar to thinking about like safety verification. Very similar. So this would now not satisfy it because there's some trace outside of P. In contrast to that, a hyperproperty would be something like this. The system would satisfy it if all of the traces of the system, again, are contained in this kind of hyperproperty, and if something outside fell, then it wouldn't be. So why I'm mentioning this in the context of autonomous CPS is it's not clear if our existing specification languages are sufficient for describing and characterizing behaviors of CPS in general, and in particular autonomous CPS. Right, so how can we characterize the behaviors of these? So the standard way that these are applied in classic computer science, so in software and purely discrete things, are with a variety of security specifications. Things like non-interference, but also some kind of non-functional specifications that we might care about, like response times and other kind of performance-related things. So that's kind of what I wanted to summarize on of some other work that's going on, of course with applications and CPS security, but maybe in being useful in describing desired behaviors of autonomous CPS, because this is strictly more expressive than just considering properties. So then it turns out you actually don't need anything beyond this. So this is as expressive as you need to be. So you don't need to consider like sets of sets of sets of sets of traces. Considering sets of traces is as good as you need to go. So we have some work in formulating a hyperproperty version of signal temporal logic that so far we weren't thinking about it too much in the context of autonomous systems, but we think this may be useful in characterizing things like robustness, so that we don't have small perturbations leading to large changes, which is what's happening if we look at what adversarial machine learning methods are doing. So we can express some things like this, these kind of robustness properties in hyper-STL, but not in normal signal temporal logic, and some other kinds of specifications as well. And this is something sort of interesting that I'll close on, because I know I'm out of time. But it turns out that, for example, Lyapunov stability is not a property, but it's actually a hyperproperty, which is sort of an interesting relation between different areas that we came across. And the intuition of this is that for local stability, so for global stability, an individual unstable execution can illustrate that the system is unstable, right? Because, okay, let's say finite time blow up, well, clearly the thing is unstable. However, you can't do this for local stability. So if you have a single unstable execution, it doesn't mean that the system is actually unstable. You just may not have started close enough to an equilibrium point. You may not have started within a region of attraction. So you may need to slice up the state space in a kind of a more rigorous, more detailed way to be able to talk about what stability and instability would mean. All right, so some interesting connection that kind of showed up that we weren't expecting when we started looking at that. So of course, thank the group and all of you and the sponsors and everyone. So I appreciate the opportunity to talk at the summer school. I've enjoyed it. I look forward to hearing a few more talks. Thank you.
Thank you very much, Tyler. Questions? Well, I'm going to use this time to ask a question.
Sure.
If you can go back to the template of hyperproperties, this idea is really very interesting. I hadn't seen it before.
Okay. Yeah.
I'm wondering if it can easily capture for all there exists unique, for example. It looks like it would do that.
Let me think.
So
So you're saying like for all traces tau, there is a unique trace
tau prime, for example, yeah. And the way we say unique usually is, of course, that if there's any other one that satisfies this property, then it's the
equal.
same one.
Yeah.
And
Yeah,
here,
I would think so by combining the other logical connectives.
yeah, because here you have a negation of the equals, and usually A implies B. If anything satisfies this property, then these things are equal. If you turn the implies into a conjunction, you negate the other side. I can't remember exactly. I guess it's usually a, do you turn the implication into conjunction or disjunction?
No, like to remove the implication?
To remove the implication.
Yeah, normally disjunction.
Disjunction,
So
okay.
A implies B is not A or B.
Okay. But here it's a conjunction, okay. But I wonder if one can still,
Yeah, so I think, I mean, I don't think there are major restrictions in the Boolean connectives.
So the conjunction that you have here is just an example, is not part of the template.
Yeah, it's just an example.
Okay.
Yeah, yeah. I didn't put the grammar.
So the key idea is
didn't
for all
put the
over
grammar.
all traces, there
Yeah.
exists a trace.
Yeah.
So with that, then you obviously can express uniqueness.
Yeah.
Then the other question is, if you had just uniqueness, if you had for all there exists, well, I guess, if you had for all there exists, would that be enough to capture all such properties? But I guess if you're free to choose the rest of the term, then that should be easy also to do. Very interesting.
Yeah. So the canonical reference is this paper on, not in the context of CPS or anything, just in the context of security, but by Clarkson and Schneider. And I think it's like 2009 Journal of Computer Security or something. But Clarkson's thesis is quite nice and has lots of examples.
Oh.
And then since then, people have worked on temporal logic extensions because they kind of did this on a set theoretic sort of way. There's a lot of topology actually in the dissertation. So particularly for establishing the completeness argument.
We need a lot of topology in this area.
So,
more topology.
Yes. So, but now there's languages like hyper LTL, so hyper properties for LTL, and then our hyper STL for signal temporal logic. And for hyper LTL, there are some verification methods, but this in general is harder, right? So this is much harder than classic model checking. So scalability of this, even for purely discrete systems, is going to be worse. But as a specification language, it's very nice. But the verification methods are very, I'd say, primitive at this point, just because it hasn't. It's been going on under a decade, right, or maybe right at a decade. So.
Very cool. Tao?
I have these questions. So when you consider the state of one trace, you consider set of traces, then we have this problem with the quantifiers. So for either,
Exactly.
so there exists and for all in terms of verification and also in terms of synthesis.
Yeah. So. So as a specification language, right, I can do whatever.
Yeah.
So the model checking methods for things like hyper LTL, and then what we've done for hyper STL, we only did falsification. And even for doing falsification, it's for a restricted class. And it has to do exactly with the order of quantifiers and what alternations of quantifiers are allowed. So the kind of typical things you'd imagine that are going to like show up with decidability of first order logic. So those restrictions certainly exist.
And also another thing is in terms of stability. So the true stability, it would require something more complex. That means that you will have to, like for all epsilon or for all delta deviation that exists. So is it the any way to simplify or approximate this and to make it more practical?
Yeah, I mean, the classic definition of Lyapunov stability, right, involves these quantifiers over reals, like what you just said. So I don't, I mean, you can allow parameters within the hyperproperty definition, so that's kind of how those are coming into play. Because if you think about a trace, like if I can quantify over all traces, and my traces involve reals, right? It's sort of like I'm quantifying over all reals, but actually maybe even more. Yeah, so that's how, in this definition of it, you're going to pull in that kind of quantification.
Okay, another question is about perception that you mentioned.
Okay.
So what would you imagine that?
For verification, or what do you?
What I mean that how can you model or how we deal with that? Like if we intend to do anything with that
Yeah.
is considered as perception and not control or decision making.
Yes. So I mean, I think the best idea so far is, the feature space thing. So let me just find. I'm just going to load something quickly, just in case I haven't seen these, and I should have put some of these in my slides, but I didn't. This video's going to load or not. I can download it more quickly. Okay, yeah, that'll work. So just for the types of attacks, if you haven't seen these things, so the image classifiers now are classifying this as a rifle, right? So these are the types of adversarial machine learning attacks that exist. And this is sort of a more nefarious one, but there are methods even changing a single pixel. And what's really neat about that one is that it's a 3D printed object, right? That they've now created a physical object that they're still fooling the classifiers with, instead of it just purely being something digital. So, I mean, perception is sort of, I think, the big question. Because I can easily say an image classifier should never misclassify something on its input. But what does that mean, right? So it's not clear how to even say what correctness is.
Yes.
Yeah.
No, go ahead.
I'm thinking about if you want to improve the situation, would you need to retrain the classifier so you can correct the classifier next time?
Yes.
Yeah, it would require modification,
Yeah,
right?
yeah, exactly.
That's so this is an example with a publicly available classifier from, in this case, Google, right? So it's.
Can you replay that video again? I assume that it was a 1 pixel attack.
No, it wasn't. It
But
was
it's
they
really
were
interesting that
applying
it's
a pattern.
Okay.
Yeah.
So it's kind of a camouflage or something like that.
Yeah. But it still looks like a turtle, right?
Yeah. So it looks like a turtle, but it should feel like a rifle somehow.
Yeah.
Yeah. So this is the one that feels like a turtle,
Yeah.
and then the other one, this should feel like a rifle.
Yeah, this is now a rifle.
Okay.
And they've done something. I don't know the details, but.
The Safari formulates the problem as like you have a controller designed with neural network, and then that controller should work for
Right.
any input. But if we don't look at the functionality of the neural networks, how they train, for example, whether or not with the new input they can train as expected, as the original design of the neural networks. How to specify this, the goal of training.
Yes. Yeah, I mean that's a good way to formulate it, I think. Yeah, but I mean how you specify correctness, I think for any of these things is a major challenge. Because I mean, even I think in the community, right, it's typically like performance criteria. So that's the standard metric that gets used, whether that's accuracy. So if you think of a speech recognition classifier, so that's mapping from audio signals, okay, so frequency spectra over time, to words. So that's the output. So the standard thing within this community that would be done is you come up with some new method, and then you benchmark against a standard benchmark set. And based on that, you characterize performance. Now, maybe eventually the benchmark sets just have all these adversarial examples, and things are sort of good, right? But my understanding, there were some defenses to some of the adversarial attacks presented in some of the machine learning venues like NIPS in the last year or two. And then, 3 months after all these defenses were presented, and it was apparently a lot of papers, like 17, 20 papers, all of them are defeated already, right? So I think it's a major issue from a specification, from a quantifying performance. Yeah. So lots of work to do. And some good research to do.
If, for example, in circuit design, they have this. They call intention, design the intention.
Mm-hmm.
So then, for example, when you do the layout, you will capture the.
I see. Yeah. I mean, maybe incorporating some of these things into the generation process or the training process. I mean, I think too. It's not totally clear yet whether the real deployments of these things are going to have only been trained offline or also have online learning, right? So once you have online learning, then maybe you can introduce examples. But I like this kind of designer intention idea. Maybe there's some way. One thing I'll mention in the context of the control systems, this doesn't really apply to perception, but there are methods that came out in the 90s, as far as I understand, out of intelligent control, that would allow you to train, like update the weights of a network online, such that you could guarantee stability of the closed loop system. So you're changing the weights for performance reasons, and essentially you can come up with a Lyapunov function for the whole closed loop system, and you characterize the way you're updating the weights of the neural network. Whatever you're doing there, you can sort of write that as a function, take the derivative of it. Now you kind of have the dynamics of the neural network update law. And then the two of these composed, you now still have stability guaranteed as you're updating for performance. And if you think about what's happening there, that's essentially a statement on the reachable states, if you will, right? It's an abstraction of doing reachability because sublevel sets of Lyapunov functions are invariants, therefore they contain all the future reachable states. So I think some type of, that's simpler than probably what's going to happen in perception, but some similar types of guarantees in the training processes. But the spec is already very clear, stability, right? But for perception, It's very simple to say intuitively, but how we'll write it down in any rigorous way is not at all clear. Yeah, so maybe hyperproperties, but it's right. Well, thanks for all the questions.
Awesome.
Good discussions.
Tyler, thank you very much for the great lectures.
Thank you.
I know you're super busy and you
I
came
enjoyed it.
a long way,
Learned. Oh yeah, well, you know.
but it was really, really great to have you
Yes,
here.
Okay.
Thank you very much, Tyler.
Thank you.
This is a small thing
Thank
from the
you.
university.
Okay.
I hope you enjoy it.
Thank you.
Back home.
All right.